Hello. So today I'm going to tell you a little bit about my experience working as a data scientist in the industrial space and why we aren't really succeeding with it. So to tell that story, I'm going to start with how I got here. So 6 years ago, I was working as a mechanical analysis engineer in the oil and gas industry. So my job was to help operators and designers understand the structural behavior of different products and offshore structures. And in January 2014, I was assigned what I look back on now as my first data science project. So the task was to take data that they had gathered during drilling operations and then validate and calibrate our theoretical wellhead calculation methodologies. So in order to do that, they gave us a bunch of data. So we had background information, things that the operators and the engineers were sharing in the form of emails. We had tons of sensor data, and it was given to us as one Excel file per day. And then we had drilling reports. So in the drilling reports, it was like events, things that they were doing, like connecting or disconnecting the riser from the platform. And so the tasks that we had to do, they're not really very important for you, but they were pretty straightforward. So we had to calculate sectional forces using all of the sensors that we had, then overlay them with events and incidents from the reports, and then try and compare that to our theoretical models. So as you do, I made a project plan, and it looked a little bit like this. So tried to understand the data, put it together, calculate some of these features, and then compare it with the theoretical models. So when I look back at this now, I think, oh, this looks pretty easy. It looks pretty straightforward. But I wasn't a data scientist at the time, and I certainly wasn't a programmer. So a lot of this work took weeks. I hadn't heard of pandas, so I basically had to learn everything about data pre-processing by trying and failing. So what would have maybe taken me days or weeks now took me months. And after 4 months, we sat down in a room with another oil and gas company that was working on the same data set to validate and calibrate their own models. So when we got to that meeting, I was immediately overwhelmed. We presented our results, and they presented their results, and they were vastly different. So I remember one of the things that they said was, oh, didn't you get this new updated data set? There was a problem in the data set that you're using. So I had to take down all of the notes about all of these things that we had to change with our data, and then go back to my local computer, change it in my script, and try and reproduce the results that they had. So this is sort of how my brain felt. There was so much data to understand. I was having to use emails as a method of versioning, and I was just really, really confused. And at the time, I was 24, so I'd only been working for 2 years, and I thought that this was just a result of my own incompetence. I felt a little bit silly, and I felt stupid, but I thought that this was normal, that this was something that I would get better at with age. And I have gotten better at it with age, but what I've realized is that these types of problems are problems that are pervasive in the industry. So we are constantly faced with people working in silos, data existing in silos, and everybody using different tools. So engineers don't use Python to look at data, they maybe use Excel. And so these types of differences in the way that we work and communicate make it really, really difficult. And so I've spoken a lot about this with my colleagues and my peers and other people in the industry, and it turns out that I'm not alone. Because even though we've gotten better and we've gotten smarter and more organized, we're still really not seeing the results that we thought that we would. And it turns out that we aren't alone, and 85% of AI projects fail to deliver the results that we're looking for. So we see that most of these projects, especially in industry, just fail to make it out of the pilot phase. So in order to understand why, I want to explain a bit about what we need to be successful. And I'm going to use this analogy of a rocket ship. So in order to get a rocket ship off the ground, or if you want to achieve your goal of understanding and predicting equipment behavior, you really need 2 major things. So you need an engine, or a powerful algorithm and a computer, and you need premium processed fuel. And if you have these two things in combination, you can really sort of achieve liftoff. But the reason that we're failing in industry is because of a lack of this processed fuel. It's not that it doesn't exist, it just doesn't exist in a form that we can use for industrial AI. And something that we're often asked by customers and other people is, well, why is it that Tesla is able to build a self-driving car, Google and Facebook are able to achieve all sorts of cool things with data? Why aren't you able to just build a model that identifies failures on equipment? It seems pretty straightforward. So to explain why, I'm going to get a little bit of help from my nephew. So Luca is 18 months old, and he's sort of the apple of my eye. He lives in Boston, and he has 2 dogs. Their names are Aegon and Zeus, and Luca loves these dogs. So he can often be found feeding them, rolling on the ground. He's always with his dogs. Sometimes he can even be found trying to drink from their water bowl. But the other day, we were FaceTiming. And so Luca isn't really very interested in me or talking to me yet. But while I was watching him play, he suddenly looked at the phone and he goes, "Doggy." And I thought maybe he was pointing to his dog at home. But it turns out I have this painting on the wall behind me, and this was on the sofa behind me. And so Luca was able to extrapolate from the 2 golden retrievers that he has at home that this abstract art was a dog. And I think that that's really incredible, that 18 months old, he's able to already create these sorts of understanding about what a dog really is. And this is why, this is something that my 18-month-old nephew can do, but it's something that almost all of us can do. So if we just go to Google, we can find billions of examples of cats and dogs and people on the internet. And that's because almost everybody is able to label these types of images. So in consumer industries, AI has been able to revolutionize them. Because they have an increase in computing power, we've seen an increase in the size of the models, but first and foremost, it's due to a vast amount of data. So we know that data is a foundational component of training models. But in heavy industry, we suffer from infrequent incidents, and we only have a handful of experts, and that means that we only have a very, very few number of examples to train models on. And industrial data is a lot more complex than cats and dogs. If we take just a single piece of equipment, like a compressor, you have maybe 1 critical failure per year to learn from. And then that 1 failure can be any of 33 failure mechanisms or 20 failure modes. And then if you wanted to get it down to the level that I think a lot of people expect, of saying which component or maintainable item it is that is actually failing, then it's 1 of 60. So it's the equivalent of having to train a model on cats and dogs and turtles and snakes. It's just a lot of data that you need. So if we were to take, a traditional supervised learning approach, and we want to say, okay, let's achieve something as great as this ImageNet Kaggle classification challenge that was almost 99%. And they had 12,500 pictures of cats, they had 12,500 pictures of dogs. What does that mean for a compressor? So for a compressor, if we wanted to use a supervised data scientist approach, and we know that we only have 1 failure per year to learn from, then you would need 12,500 years of operational data. You would need almost 400,000 years of operational data just to say the type of failure mode and mechanism, and then millions of years if you wanted to get down to the level of specific component. And there's no operator in the world that has access to all of this data or the time to label it. And before you say that that's a very extreme analogy, maybe we should try data-driven approaches, we have. And they're really not very good either. So if you said, on a platform, you have 20,000 sensors, and we think an anomaly or an outlier, a failure, is anything that happens 0.01% of the time, that would be the equivalent of raising 50 alarms a day. And most of these operators don't have just one platform. They have 10 or 15 or 30 that they have to monitor. So you're basically raising 1,500 alarms a day. And if you can find an engineer that's willing to go through those thousands of alarms, then I'll be really, really impressed. But most of them aren't. And they'll also tell you, and I know this based on experience, based on delivering these sorts of anomaly detection models, an outlier is not the same as a failure. So data is the foundational component of training models, and we have two major problems. We have infrequent incidents and handful of experts. So how do we address it? So maybe you want to make your equipment fail more often, so you can have more frequent incidents to learn from. I don't think that there's very many people that would want to break this couple $1 million equipment and then lose millions of dollars in lost production. So I don't think that's an option. Then handful of experts, how do we really address it? So I think that there's three major things that we might be able to do. So the first is to work closely and methodically together. So this sounds very, very obvious, but a lot of industrial operators are focusing on collecting lots of data and not necessarily putting that data together in a way that gives meaning. So you should collect lots of data, but you should collect the data with intent. So rather than trying to, boil the ocean, start with one specific problem. If you start with a compressor, think about how that's going to scale. And it's probably going to give a model that has more value if you do it on 100 compressors than if you did it just on the single compressor. So I think that it's important to take the time and the investment to really put together the data in a meaningful way so that you will be able to scale your machine learning. And second, engineers have been around for a very, very long time. They've been working on theories and physics-based models for ages. And this is the type of data that we should really be using. We should be making engineered features. We should utilize known KPIs as proxies for ML. So an example that I have is from a problem that I worked on before, which was on predicting heat exchanger maintenance. So they would have to clean the heat exchanger whenever it got filled with some microorganisms, so they would have to clean it. So we tried to build a model that would predict when they should clean it based on historical cleaning patterns. But on a heat exchanger, you can calculate things like performance, and you can calculate heat capacity, and that can be a perfectly good feature rather than having to do a complex machine learning model that isn't necessarily going to give you new information. All it's doing is really relearning physics-based models. And third, this is really a team sport. I guess you guys have probably seen these, the cartoons of everything that a data scientist needs, and it's just unrealistic to expect one single person to have all of this knowledge. So it's really about collaboration. So including the engineers and the operators, the people that really fundamentally know the equipment and are able to tell you about what they need and what they expect. I've also found that sometimes they don't really want a deep learning model. They just want to put a model that they have in Excel up into the cloud so that it's able to be monitored. So these are things that, that we can do pretty straightforward. I hope that you guys will maybe find me today and tell me how you guys are making predictive maintenance work. If we don't sort of come together and change the way that we're working and, have better data and collaboration, I think that predictive maintenance will continue to be a fantasy. And I hope that that's going to change. Thank you.